So we're back to the question at hand, and that is whether or not this collision is elastic or not. And the first thing we want to do, of course, is identify the system as before. So, of course, the system here is comprised of the two objects together. And the question boils down to whether or not the initial kinetic energy of the whole system together is equal to the final kinetic energy of the whole. And then we can unpack this and express it as the initial kinetic energy of mass 1 plus the initial kinetic energy of mass 2. That's the left-hand side. The right-hand side would be the final quantities. So the final kinetic energy of mass 1 plus the final kinetic energy of mass 2. And so the question then amounts to showing that this equation is true, or checking to see if it is. So first of all, we can go ahead and either multiply through by 2, or think of just canceling off these factors of 1/2, since every single term has one. Moreover, we do know that the masses are equal. That's what we're given. And if they're all equal, so if M1 and M2 are the same, then what I could do is replace those with some letter M without a subscript, and then cancel those off in every single term as well. So far our equation has simplified considerably. Finally, we note that V2 is equal to 0, V2 final is equal to 0. So immediately this last term here we can eliminate. So that's equal to 0. And then we can go ahead and plug in the values of these velocities. So V1 initial, V2 initial, and V1 final. And the problem then amounts to showing that 3 squared, because we're plugging into these velocity quantities, 3 squared plus 4 squared is equal to 5 squared. And that's indeed true. Both sides equal 25. So we've shown that the initial kinetic energy is equal to the final kinetic energy, and therefore the kinetic energy is constant throughout this collision. And indeed, it is elastic. Now let's look at something interesting. So a 1D elastic collision, and 1D in this case, of course, means that we're taking in this particular example, a cue ball that's approaching or coming in towards an 8 ball that happens to be coming in towards the cue ball itself. So both moving in opposite directions, and they're going to collide. And we're assuming that they're going to collide in such a way that the back reactions only act in one single direction. So we can define a single direction in the initial case and a single direction in the final case. Now, we have to form some equations to be able to solve for whatever we might be interested in. The first thing we want to do is remember that momentum is constant throughout the process, or throughout the collision. So we can state that in mathematical form. We simply say that the momentum of mass 1, which is the cue ball, initially, plus the initial momentum of mass 2. So as the sum of the two gives me the total initial momentum, and then that's should be equal to the total final momentum. Then, of course, we can also say, since we are taking this to be an elastic collision, we can make a similar statement or analogous statement for kinetic energy. And we say that the sum of the kinetic energies initially has to be equal to the sum of the final kinetic energies. Now, something interesting happens in one dimension. First of all, note that these vector quantities, the velocities, actually reduce to having one single dimension involved. So a single component. And here we can think of that as the x direction. And on top of that, something else interesting happens. We obtain another equation, and it looks a little peculiar because it's an equation that describes the x components of the final velocities, x components of the initial velocities, and they're combined in a sort of a strange way, a non-intuitive way. So we see that there's a difference involved in both cases. Now, this arises if we do further, deeper analysis and think about Newton's laws. For example, we can think about the Newton's second law, sum of the forces equals mass times acceleration. We can also incorporate Newton's third law, that when there's an interaction, there's going to be an equal and opposite reaction force involved for every force applied. And if we study those in more detail and combining that analysis with the idea that we only have a one-dimensional problem, then what we would find is that there would have to be a flipping of velocities, so to speak. That simple condition is there partly as well because we have to have constant kinetic energy throughout the process. So, without going into too many details there, what we would find is obtain this equation, and it's interesting that we could, of course, note that this is in terms of components versus magnitudes, but we can express it in terms of the magnitudes of the corresponding velocities. And the way to do that, of course, is to think about maybe this term right here, which is V1 final. So it corresponds to this. And it's a component, but the component itself is really equal to negative the magnitude of V1 final. So we think of the magnitude of V1 final, which is the length of this vector, but it points in the negative x direction, since we've designated x to be positive to the right. And so we can make this substitution. Similarly, for V2 initial in the x direction, we can make this substitution. So the step here is simply going from the components, individual components initially and finally, and then coming up with an equation that involves the magnitudes of velocities. And finally, distributing the minus signs, we end up with this equation here. So the sum of the magnitudes in the final case equals the sum of the magnitudes in the initial case. So far, what we've done is sort of develop three equations for this problem. And now let's move on to a specific problem that involves those equations. And let's look at this arrangement. We have two masses, M1 and M2. And we can look at the initial situation off to the left here, that both masses are approaching each other with their own independent velocities. V1 initial is pointing this way, V2 initial pointing this way, and we have some angle that basically describes the orientation of this line of interaction. Well, the final scenario looks very similar, but of course, M1 is going in the opposite direction than its initial incoming direction. M2 also is moving in its opposite direction to its initial incoming direction. And we take this angle to be the same as the initial angle here. So the orientation of this interaction is the same as this one. And therefore, we can apply the idea that we just worked through, or that we just discussed, and which applies, of course, to one-dimensional problems. And again, it's good to remind ourselves that although this occurs in two dimensions, the actual motion we're assuming is just along one single line, one single direction. So, as usual, we define the system as being the two objects together. X direction we can take to be in this direction if we like. And as long as we're consistent with that direction throughout the problem, then we should be okay. Now, the statement about constancy of momentum is simply reduced to momentum of the system initial in the x direction equals momentum of the system final in the x direction. So secondly, we could bring in that odd-looking equation from the previous slide and then equate the corresponding x components from the previous slide, and then we get these interesting differences between V2 final x and V1 final x and V1 initial x and V2 initial x. So between these two equations, we have enough mathematics, or I should say we have enough equations really to be able to solve then for V1 final, which is what we were looking for. Now let's move on to the bigger picture and sort of summarizing what we've learned so far. So the bigger picture involves something that we call conservation laws. So conservation laws, if we think of them in terms of universal statements of mathematics about physical processes in general. And we can sort of get an idea of what we're talking about here by returning to, first of all, the work energy theorem, which is off to the left, and the impulse momentum theorem, which is off to the right. As we've seen, there are strong similarities between these two. And of course, the work energy theorem, just to recall that the total work done changes the energy of the system. Well, that's what this is saying. So the left-hand side is the work done on the system, and the right-hand side is the change in energy of the system. And analogously over here, the impulse momentum theorem basically says that the net impulse applied to the system is the thing that changes the linear momentum of the system. So in both cases, we can take the system to be everything if we like. So maybe in some idealized sense, everything in the universe. And if we do that, then energy and momentum are both constant. So in other words, if I make my system large enough so that it excludes all other forces from the outside, or I should say, it includes all things that may be acting on it, so that any processes occurring are actually contained within the system, then doing that means that the left-hand side of both of these equations has to vanish, has to be zero. And when that's the case, then we have conservation laws that state that the total energy of a system is constant or conserved. Also, the total momentum of the system is conserved in some absolute sense. But of course, in more practical ways of looking at things, in fact, most physical problems require this because we can never really be 100% sure that we're including everything. We can say that by choosing a smaller system, we can have the energy momentum of the system change. And if that's the case, then of course these equations just basically give us the ways in which that energy or momentum changes. So they give us a prescription for calculating that change in energy of the system or momentum. So in keeping with this more larger picture perspective, here is a particular experiment that was performed, let's say, probably towards the beginning of the 20th century. And we can look at carbon-14, and it's known to be unstable and to decay into nitrogen-14. And that, in essence, is including a single electron that goes shooting off in some other direction. So carbon-14 atom, then experimentally we can detect this particular process or decay. So nitrogen-14 plus an electron shooting off in some direction. Well, first of all, we note that in these experiments, it's often the case where the electron and the nitrogen atom are moving in such directions and with such speeds that these things are hardly conserved. So the total energy of the system does not equal zero. I should say the change in the total energy of the system doesn't equal zero. So total energy changes, but also total momentum changes as well. And the way we've illustrated this process indicates that. So given that nitrogen atom moves off to the negative direction horizontally, but the electron shoots off at some diagonal direction. And from that, we can see that initially the carbon-14 atom, because it's stationary, if that's our assumption, the momentum of this carbon-14 atom is zero. Well, the final momentum of this pair, first of all, we don't quite know what it is because we don't have exact values to calculate, but just from the qualitative aspect of the diagram, or the little illustration here, we can see that nitrogen 14 moves off in the negative x direction. This moves diagonally. And so there seems to be an offset in momentum, just purely from a qualitative analysis. Well, this is, of course, fixed if we assume that there was another particle, possibly, that we simply didn't detect. So there's an electron that goes off this way, but we're making an assumption that there was another particle somehow, for some reason we couldn't detect or we weren't aware of, and it moved off in this lower direction here. And the reason for including that hypothesis is because momentum isn't conserved specifically in the y direction. So the electron acquires a certain amount of momentum in the positive y direction, but that leaves absolutely no momentum moving in the negative y direction. And we would need that in order to ensure that momentum is constant throughout this process. So it was originally hypothesized that there was indeed some mysterious particle that moved off in this lower right direction that was carrying the opposite momentum of the electron moving upward this way. So this particle down here, the lower particle, was presumed to have the same momentum in the y direction as this electron does here, but opposite in direction, of course. And of course, that did lead to the discovery of the antineutrino, or really for a long time it was simply going to be a hypothesis, but it took care of the problem. And of course, this is an accepted hypothesis today. And the process here of decay is what they call beta decay. So this concludes this block, or this, I should say, this section of block 6, so 6.2. And we will see you next time.